Namaste everyone. Welcome to ray optics class. We have been discussing various aspects of light, like refraction at plane surface, refraction at curved surface. So just in the previous class, we have discussed about how does a ray of light undergo refraction in a curved surface. Now the next derivation is lens maker's formula. But before going to that lens maker's formula, better we solve one or two problems regarding this curved surface, because the lens maker's formula is that derivation depends completely on the refraction at curved surface. You have to apply it twice. So if you get a knowledge of how to apply the formula in different occasions, then it is better to understand, or it is easy to understand the next derivation, that is lens maker's formula. So we will solve one or two problems, then go to the lens maker's formula in the next class. So how to apply that formula, what we have derived. And before starting the problem, let me recap what we have derived. So we had a convex spherical surface like this, and there was a point object like a source of light, for example, small bulb. One ray of light moving straight like this. So this is the part of a sphere, and here is the center. So one ray of light incident normally, because any normal, if you want to draw here, you have to draw a line along with the along the center. So this ray of light is along the normal itself, so angle of incidence is 0. It passes undeviated. Another ray of light incident like this, it bends and it is moving from rarer to denser medium, say air to glass. Then it should bend towards the normal. Where is the normal? Normal is here. Any line passing through the center at this point is the normal to this surface. So this ray of light, which was moving like this, bends towards the normal and meets the principal axis here. So this is the image, right? That is what we have followed. And the formula connecting them is refractive n1 by minus u plus n2 by v is equal to n2 minus n1 by r. This is the formula. And remember, this formula shouldn't be by-hearted as it is. So you must know what is n1. n1 is the refractive index of the medium where incident rays are present. Incident rays are here, so this is the refractive index. n2 is the refractive index of the medium where refracted rays are present. Refracted rays are here, so this is n2. Every time you have to use the same condition. Sometimes this may be the medium where incident rays are present, we don't know. And the speciality of all the formulas which are derived in the optics is you can apply to any case. For example, we derive that we say that lens makers mirror formula 1 by f equal to 1 by u plus 1 by v. That is a single formula, but we apply it to all the cases of image formation, whether concave mirror is forming real image, whether it is forming virtual image, whether it is a convex mirror. For every condition, that single formula is useful, because every time we apply the sign conventions. Now you see this formula. This formula is derived for this condition. Sir, if the object is so close, see, there is no guarantee that the image is real always. Suppose the object is very close, there may be a chance that this ray of light will not bend too much. Of course, it will follow the laws of refraction. When it moves from rarer to denser medium, it bends towards the normal, but towards the normal may be only this much. If the ray of light bends only this much, in the last class at the end I was discussing about this. If the bending is not enough to meet this ray, now these two rays will never meet, right? Because they are diverging, they are moving away. Then this ray, if you produce it backwards, I will just change like it. Now the rule is obeyed, it has bent towards the normal. The ray which was moving like this, you can see the dotted lines here. Ray which was moving like this has bent towards the normal, but bending is not enough to meet this, so real image will not be formed. Now you have to produce this ray backwards so that it appears to come from somewhere here. Now the image is here. So that is also possible. Now the question is, this formula has been derived for this image. Can you apply this for this image? Definitely. How? Because we have to apply sign convention. So, and another thing, suppose this surface is not convex. If it is concave like this, sir, can we use this formula? Definitely. Just use the sign convention. So that's why, even though the formula is derived using sign conventions, because all minus u, v are obtained by applying sign conventions in the derivation itself. Again, when you apply it to the problem, again you have to apply the sign conventions, because in that situation where the image may be real, may be virtual, maybe the surface convex or concave, whatever the condition is, this formula holds good. provided you apply the sign conventions again. So usually students get a doubt that, sir, while deriving the equation we have applied sign conventions. What is the need of applying sign conventions again in the problem? Because it should be suited for the situation of the problem. The situations may be different. So as if in the mirror formula, which is suitable for all the conditions. Otherwise, if you were not ready to apply the sign conventions again in the problem, hoping that this is already applied while in the derivation, if the situation was so, for every condition, when the concave mirror forms the real image, you should have a formula. When the concave mirror forms the virtual image, you should have another formula. When the concave mirror or convex mirror forms the image, another formula. So you should have different formula for different conditions. That is a headache. Remembering one formula itself is a headache for us. Then how do you remember different formula with the similar notations but different signs, plus, minus and all. So in order to reduce this, we have a single formula, we have a set of sign conventions, applied to the present condition, you will get the answer. So even though formula is derived with the sign conventions, while applying it to the problem, again you have to apply the sign conventions in order to get the condition in the situation in that particular problem. Okay, that is one thing. And another thing to remember the formula is, best way of remembering the formula is work out problems. You work out problems in that formula, automatically the formula gets embedded, pressed in your brain. And don't by heart it too much, you will forget it. So apply it to the problem. So best way of remembering a formula is solving problems in that formula. Best way of remembering a derivation is teaching that derivation to your friend. Teach that derivation to your mother, father. Whether they understand it or not, that is the secondary. You will understand it better. So that is the best idea. So teach it to the others. Suppose your friend comes to you seeking some doubts, just explain them more than what is needed. Then you will understand it better, whether they follow it or not. So now we will solve this problem. First one, we will go to the first problem. Light from a point source in air falls on a convex spherical surface or glass of refractive index 1.5 and radius 0.2 meter. So we will underline the data. Refractive index 1.5, radius 0.2 meters, and object is kept in front of it. Image is formed at a distance of 100 centimeter. Image is formed at a distance of 100 centimeter from the glass surface. That in the direction of incident light, calculate the object distance from the center of curvature. So you have to find out object distance, that is the question mark. From the center, okay, that we will take care of later, because all the distances are measured from the pole, but we will take care of while writing the answer. So it is a convex spherical surface. Let me draw the diagram here. Hope you are looking into the both parts. So you take a convex spherical surface. You know the condition. Object, suppose somewhere here. It may be inside also, but they are particular here. Object may be inside the glass surface also. Whatever is suppose you have a paperweight. Inside the paperweight there will be some flowers like arrangements. If you look into that, that is the object. Now it is in front of the spherical surface. A light from a point source in air, refractive index 1, falls on a convex spherical surface of glass of refractive index 1.5 and radius, okay, I will come, you need not complete this, just for the knowledge I do that. So this is 0.5 meter, 0.2 meters. So shall I take it as 20 centimeters? Radius 20 centimeter. Image is formed at a distance of 100 centimeter from the glass. Okay, so that is the same condition, that a ray of light here and here, this is the normal, and the ray of light, instead of moving like this, bends like this, and image is formed at a distance of 100 centimeter from the glass, this pole, from the glass surface, that means pole, in the direction of incident light. That is a clue given by them. Image is formed in the direction of incident light, not to this side, right? So what is the position of the object? Now you know the formula. N1 by minus u plus N2 by v is equal to N2 minus N1 by r. So according to the knowledge, according to the situation, you apply the problem. Hope you can see here and here, both sides, right? Okay, now refractive index of the medium where incident rays are present, air. Since this is air, it is told in the formula problem clearly. So N11 by negative in the formula itself minus u, and that has to be found out. We don't know what is u. This minus is in the formula itself. Of course, you can come to a conclusion. If the object is in air, definitely if you divide this into Cartesian coordinates like this, like this. This comes to the left hand side, this comes to the right hand side, so this should be negative. Finally your answer should be negative. You should naturally get U as negative. But this is formula negative plus refractive index of the medium where refracted rays are present. This medium, refracted rays are in 1.5 divided by image distance. Image is formed at a distance of 100 centimeter in the direction of incident light, right side. It is plus 100. I will convert everything to centimeters because you have a distance. Suppose this is in meter, let everything be in meters. Suppose this is in centimeter, let everything be in centimeters. Is equal to refractive index of the refracting medium, glass, minus incident medium by radius. Radius is 20 centimeters from here to here. That is also on the right hand side. So from here, this is on the right hand side, that is 20. Plus 20, no negative. So object distance, we should get it as negative. This is formula negative itself. 100 centimeters, it is on the right hand side, image. 20 centimeter, right hand side. Now solve this one. 1 by minus U plus, I will multiply and divide by 2 because I don't like any fractions in my problem. I convert them into whole numbers. Okay, I don't like any fraction to appear in my problem. So this is 0.5 by 20. Okay. Now 0.5 is half, right? Half is 0.5. So 1 by 2, that is 1 by 40. So I write this as 1 by 40. Now what is minus 1 by U? Shall I write it here? I hope you can see that. I will write it here. Minus 1 by U is equal to 1 by 40 minus 3 by 200. 3 by 200. Can I take 200 as common? Yes. That implies minus 1 by U is equal to, better you write 1 by U always, because if you write equal to and write the answer, you hope that that itself is the answer. That is not the answer because it is 1 by U, it is not U. So minus 1 by U, 200 common, 45 times 5 and 200 1 times minus 3. So what is this? 2 by 200, but this is 1 minus 1 by U and this is 1 by 100. So what is U then? Minus 1 by U is 1 by 100. U is equal to minus 100 and it is centimeters. That means object is kept at a distance of 100 centimeter from the, which is negative, this side. We got the correct answer. 100 centimeter from the surface in air. But their question is, calculate the object distance from the center of curvature. So every time in the examination, when you do the problem, after completing the problem, underline the answer and check, go back to the problem, see whether you have answered to their question or not. That is very important. You get the answer, you are very happy, and you say Jai and go to the next problem. You have lost 1 mark because you have not answered to their question. What is the distance of the object from the center of curvature? From here they are asking. That means that also contains last 1 mark in the scheme of evaluation. You must be very careful. 20 plus 100. So answer to their question is 120 centimeters. Am I right? It is from the pole, because our sign convention is all the distances are measured from the pole. But they are asking this distance. So 100 plus 20, 120 centimeters. So object distance is 100, no doubt. But another confusion here is, sir, we got object distance as negative. Shouldn't we subtract minus 120? No, because this negative sign has only the significance that object is kept in front of the surface in air. But when you take the total distance, think in your general knowledge, will you subtract these two? Never. It is 120 itself. So it cannot be 80 or minus 80, something like that. It cannot be. See the reality here while coming here. Don't apply sign conventions everywhere, right? So this is 120, distance of the object from the center. Okay, one problem is over. We will go to the next problem. Here, a point object is, hope you can see this problem, right? So read the problem. A point object is placed. I'll rub this. You can note down these problems later. You need not write it because I have sent a PDF notes. In that problems are there. Okay, need not worry. You can write it later. Just read the problem now. Don't keep it on copying. It is there in the PDF. A point object is placed in front of the surface of a glass sphere of 0.25 meter radius along the diameter. Find the position of the final image. refractive index of glass is 1.5. This is a very, very important problem now, because this will teach you how to go for the derivation, next derivation. This problem itself will tell you how will be the next derivation. Okay. Even the next problem, of course, next problem is based on the same method of solving this one. A point object is placed in front of the surface of a glass sphere of 0.25 meter radius along the diameter. So it's a glass sphere. I will draw the diagram here only. Okay. This is a glass sphere, say. A point object is placed in front of a glass sphere along the diameter, and distance is not given. Yes, 1 meter from the surface of a glass sphere. That means from the pole. If it is not from the pole, they must mention it from what distance you have to keep. A point object is placed in front of a glass sphere of 0.25 meter radius. Radius is 0.25 meter. So this is 0.25. I'll write everything. This is also 0.25. You will come to know why do I write both the radii. And find the position of the final image. Refractive index of this is 1.5. Now the thing is, here there may be two chances. One is, as usual, suppose this is a point object, say a bulb, a small bulb, an LED bulb, say. It emits light one like this, and that passes undeviated because it is passing through the center. It is normal incidence. Another ray of light incident somewhat like this, and bending like this and forming the image here. That is also possible. But there may be another chance that this first surface, there are two surfaces here for the glass sphere. One surface is this one, and another surface is this one. Sir, what about the second surface? I will name them 1 and 2. Won't the second surface get a chance of refracting the rays of light? Yes, possible. If this ray is not bent too much away from the normal, of course, towards the normal, because normal is here. If this ray is not bent too much, but it is bent towards the normal, but bending is not enough to meet the principal axis inside the glass sphere itself. By the time this meets this ray, suppose the second surface starts. That means glass sphere has got second surface. Now this ray got a chance of undergoing refraction in the second surface also. Second surface will bend it and form the image here. This is the situation, right? So there may be the first chance also, the ray may be bent too much towards the normal and it may be meeting the principal axis here itself. Second case is it may bend a little bit but towards the normal only, but that bending will not be enough to meet the principal axis inside the glass itself. By the time it meets, it will come across the second surface, and second surface will bend the ray again. Now we have the formula n1 by minus u plus n2 by v is equal to n2 minus n1 by r. We have this formula. Now if you want to use this, you have to use it twice. Once for this surface, another for this surface. We will have to see now. Suppose it meets the principal axis here itself, no problem. But if it continues, we have to apply that formula 2 times. Now here is the logic, and there is a beauty here. And you have to apply the formula in a different way. Okay, now let me consider the first surface. You ask the first surface, surface 1, surface 1. Are you receiving any ray of light? Yes sir, there are many rays of light coming from the object. And do they fall like this? What did you do with the rays? Sir, I bent them towards the normal and I sent them inside my medium. And do you have any object in front of you? Yes sir. Where is the object? How do you find out the object? Surface 1 says, sir, I am receiving 2 rays of light. I will produce them backwards and I get it here. So this is the object for me, sir. Okay, now imagine that this glass sphere has no second surface. Its second surface is absent. What do you mean by second surface absent? If the surface is like this, other surface is absent. That means it is full of glass like this. Let me continue the glass. This has not been curved at all. If I take a diamond and if I cut it here and polish it, then this is ready. Now the second surface is absent. Okay, the principal axis is like this. If I draw the same situation here, here is the object and a ray of light incident along the principal axis passes undeviated. This is the center. And a ray of light incident like this will bend first like this. But there is no surface here. It is glass, continued glass. What will happen? This ray will continue and it will meet the principal axis here. This is the image formed by the first surface alone, not with the help of second surface. Suppose second surface is also present it will also cooperate with the first surface. It will bend it again and form the final image here. But this is I1, this is the final image I. Right, the second surface somewhere here. This is final image I. So, can I show this ray here, sir? No, I can't, because there should be a refraction here, right? But if I want to show this ray, shall I continue this with dotted lines, which is not possible in this because there is a second surface. So shall I call this as I1? Image formed by the first surface alone is because of this ray continued in the glass itself. But we don't have glass here onwards, we have air again. I think it is air, nothing is told about that in the problem. So this is air. So this will continue and we will meet the principal axis at I1. That is the image, okay? Now, this is the image formed by the first surface alone, remember. That picture is seen here. So this ray might have moved straight and to meet the principal axis here, right? So that is this one, I1. Now we will apply the formula for the first surface. Let us see where this image is formed. I call this as V1, image distance V1 from the pole of this surface. So I will call this as V1. Let us see what is V1. Suppose we get V1 within 0.5 meters, that is diameter. Within this diameter, if we get V1, we are safe. Image is formed within the glass sphere itself. Suppose this V1 goes beyond 0.5, then it goes outside. That is the meaning. So let us concentrate on the first surface only. Shall I write it here? I think we can see it here, right? So first surface, for surface 1 I will write. For surface 1, formula is n1 by minus u plus n2 by v is equal to n2 minus n1 by r. That is the formula. n1 by minus u. What do you mean by n1? Refractive index of the medium where incident rays are present. This one, 1. Minus u, minus in the formula and our own minus 1, because this is 1 meter, you know it, 1 meter, this is 1 meter, object distance, it is given, right? Placed 1 meter from the surface. So n1 by minus u, minus of minus 1. Minus because if you divide it into the coordinates, it comes to the left hand side. Plus refractive index of the medium where refracted rays are present, that is 1.5 divided by image distance, don't know, v, is equal to refractive index of the refracting medium, this one, right? That is 1.5. It is completely 1.5 because this surface is absent. Refracting medium minus incident medium, 1, divided by radius. Radius comes to the right hand side, right? Radius is 0.25. Is it okay? Substitution is very important now. Refractive index of the medium where incident rays are present, air. A negative formula, negative. Object distance minus comes to the left hand side because you have to start from the pole, come to this side. Rays of light are traveling on the right hand side, opposite to the direction of incident light. Our own minus, sign convention minus, plus n2 that is 1.5 divided by v, image distance, that is not known. Difference, refracting medium minus incident medium by radius. Radius is positive, right hand side. Okay, because here to here it's radius. Okay, this is plus 1 now. Plus 1, 1.5 by v is equal to 0.5 by 0.25. Am I right? Of course, this ratio I am very familiar, even though it is fraction. Or you multiply by 100 and divide by 100, what you will get? 25, this is 50. So shall I write it as 2 times? So this is V1, right? Sorry, this is V1 because now the first image distance is taken as V1. Okay, 1 plus, I will take this one to the other side. 1.5 by V1 is equal to this one to this side. This is 2 minus 1. That implies 1.5 by V1 is equal to 1. What is V1? V1 is equal to 1.5 meters. We got it as 1.5 meters. Oh, now it is going outside the surface. That means if the second surface itself is not formed, only first surface is present, there is no air again, it is complete glass, the first surface alone would have formed the image at a distance of 1.5 meters from the pole. And that is away from 0.5, sir, here. 0.25, 0.25, 0.5. It is 1 meter still away. That means second surface will definitely get the rays to bend back. So it will receive the rays. It will not meet the principal axis just before going to the second surface. It will be going outside the second surface. Now the question comes, so what about the final image? So final image is not at 1.5 meters now. Now the thing starts here. Now you ask the second surface. So shall I name it as 1.5 meter? And if this is 1.5 meters, now for the second surface, now the reality comes here. You ask the surface 2. Surface 2, what are you doing? Sir, I am receiving 2 rays of light. What are the 2 rays of light? One is this one, sir, and another is this one, sir. What did you do with the 2 rays? Sir, I bent both the rays and I made them to meet here, and I am forming the final image here, sir. That is my job. Okay. Surface 2, are you having any object? We asked the same question with the surface 1. Do you remember? When you ask the question to surface 1, surface 1, where is the object? Surface 1 answered us that, sir, I am receiving 2 rays of light like this. I thought they are coming from the object, so I produced them backwards. Oh, they met here, so this is the object for me. What about the surface 2? Ask the surface 2. Surface 2 says, sir, I am receiving 2 rays of light, sir. One is like this and another is like this. They must be coming from object, so I will produce them backwards, sir. But they are not meeting at all. They don't meet if you are producing them backwards. Now surface 2 is in a confusion. Sir, these rays, when they are produced backwards, they are diverging. I am confused whether they are coming from an object or not. What are all the 2 rays received by the surface 2 don't meet in the backward direction. You produce them forward. Definitely they meet here, right? So this is the image of the first surface, but for the second surface it acts like an object. This is the beauty of this problem. So image formed by the first surface here, when you cut this glass sphere here and remove the other part, immediately air occupies this space and the ray gets bent here and the final image is formed. So for the second surface, these 2 rays are the incident rays, and these 2 rays are not coming from any point here, but if you produce them backwards, they are coming from this point. They appear to diverge from this point. So this is the object for the second surface. Hope you have followed. Whenever we receive light, if that light is reproduced backwards, if they meet at a point, that should be the object. And when you reproduce the 2 rays backwards, if they don't meet, if they don't meet, then the image will be, the object will be acted by some other point. This is the point here. So for this surface, these 2 rays never meet backwards, but if you produce them forward, they meet here. So in a common sentence, if I say, it is very simple. Image produced by the first surface acts like an object for the second surface. That's all. Very simple. Sir, can an image act like an object? Definitely. That is possible. I can give you an example. If you go to a barber shop or a beauty parlor, a mirror will be kept in front of you, another mirror from backside. You are standing in between. You see multiple images, right? And that is formed because suppose you have 2 mirrors like this, bent and kept like this. And if you are standing here, you see multiple images. Reason is very simple. This mirror looking at this object forms an image here, okay? And this mirror looks into this image and forms its image, and it feels that this is an object, and it forms the image here. And this mirror looking into this object, it forms an image here. This mirror looks into the image formed by this mirror and treats it as an object and forms its own image somewhere here. So this keeps on multiplying. Image formed by one mirror may act like, or it will act like, an object for the second mirror. That is possible. So similarly, image formed by the first surface alone acts like an object for the second surface. So if you want to write any object distance for the second surface, you have to write it from the surface pole, that is from here. So for the second surface, this is object distance, and object distance is, this is 1.5, this is 0.5, 0.25 plus 0.5, this is 1 meter. Okay, now if I draw a diagram only for the second surface, this is glass. Don't know what is happening earlier here, forget about what has happened in the first surface. take a ray of light. So this is glass, this is 1.5. One ray coming like this through the center of this surface, right? The center of this, okay, it is like this. This is the center and this is the principal axis. Okay, I'll rub this. Now one ray moves like this, right? And another ray is hitting like this. And this is the surface now which is of interest for us. And these two rays are not allowed to produce an image here, because that was the work done by the first surface, that was I1, and this is at a distance of how much? 1.5 meters from the sorry, it is only 1 meter, because 0.5 meter we have to deduct from this one, it is 1 meter, and these two rays were made to bend here and meet here, and this is the final image. Now you have to apply the formula once again, same formula, but everything will be changed here. You see the beauty of this problem. Refractive index 1.5, refractive index 1. Ask the second surface, where are the incident rays? Sir, incident rays are within me itself, because the surface is here. It is in the refractive index 1.5. This is the medium where incident rays are present for the second surface, remember. So N1, shall I write it? I will write it on the other side. N1, refractive index of the medium where incident rays are present, 1.5. It is not 1 now, because inside the glass for the second surface, divided by negative of, formula negative itself, object distance. See, ask the second surface once again, where is the object? Sir, if I produce it backwards, they don't meet at all. So I will produce them forward, they meet here. So the image formed by the second surface acts like an object for the first surface. That distance is 1. That comes to the right hand side, plus 1 itself. Am I right? That is 1 itself. Of course 0.5 you have to remove out of 1.5. Plus refractive index of the medium where refracted rays are present. After the rays fall on the surface, they are refracted back to air, 1 divided by image distance. That is the final image distance here, that we don't know where the image is formed, right? That is the final image distance, V. That is what we have to find out, is equal to refractive index of the medium where refracted rays are present, sorry, 1. N2, refractive index of the medium where refracted rays are present, minus where incident rays are present, divided by radius of curvature. Again the beauty, you see, this surface is like this, radius comes to the other side, 0.25 only, but on the left hand side for these rays. Last time the radius was here, this was the origin, and it was lying here. Now it is lying the other side. So minus, radius is minus, it is to that side, minus 0.25. Okay? Now we have to find out the final image. That is the thing, and okay, where we are now. Yes, we have to solve this. 1.5 divided by minus 1 plus 1 by V is equal to minus 0.5 divided by minus 0.25. Of course, you compare it to the other case. Finally, it has become the same, right? This has become negative, this also has become negative. So this is 2 times. Negative sign cuts off, right? 0.25 2 times. So multiply and divide by 100, 50 by 25. So what you will get then? This is minus 1.5. So 1 by V is equal to, this minus 1.5 becomes plus 1.5. 2 minus 1.5, correct? Hope we are going right. 2 minus 1.5, yes, it is right. 2 minus 1.5 is 0.5. 1 by V is equal to, did we go wrong anywhere? Refractive index of the medium where incident rays are present, glass, divided by negative of object distance, correct. 1 meter is on the right hand side, because this is serving like object, plus refractive index of the medium where refracted rays are present, air, divided by the image distance, V, correct. That we don't know, that should be here, is equal to refracting medium minus incident medium divided by radius minus 0.25. Radius is on the other side, yes, it is correct, 1.5 by minus 1, and this becomes plus, right? Yes, that is the only thing. So 1.5 by minus 1, this is minus 1.5, and that becomes 2 plus 1.5. So what is this? So this is 3.5. V is equal to 3.5 comes to the denominator, 1 by 3.5. So let me see what is 1 by 3.5. It is, so if you use your calculator, you will get the answer. 1 by 3.5 gives 0.2857 answer, 0.2857. This is the answer. So what is the final image position then? So again the question is here to find out the image distance from the final image, that's all. Okay, where is the final image? The final image is formed at a distance of 0.2857 centimeters, that is this distance, am I right? Or this one here, from the second surface. Suppose you are asked to find out final image distance from the first surface, then you will have to add 0.5. So final answer you should write like this. So I will rub this one, this is not needed, this is only a supporting diagram. Okay, so final image is formed at a distance of 0.8257. You see, you got the answer as positive, correct? You got the positive answer, right? Why? What is the meaning of positive? For this surface, it is on the right side. It is correct. It is final image is here. 0.2857 meter from the second surface, or at a distance of 0.2857 plus 0.5, right? You have to add this. From here, this one, or 0.2857 plus 0.5, or 0.7857, correct? If you add 0.5, it will be 0.7857 meter from first surface. Or you can write it from the center also. You can write it 0.25 plus 0.2857, anything. But you must know how to answer for the question. But if it is asked only what is the image position, that means you have to find out the image distance from the first surface. This is the beauty of this problem. So this exactly is carried on to the next derivation, that is lens maker's formula. We will solve this problem later. This problem is pending. I will solve this later after working out or after deriving lens maker's formula. That is better, so that we will have a little bit of explanation there also, right? So that is a little bit different problem, and take it as a homework now. That is the best one, right? Take it as a homework and try to solve this, and message me the answer to, did you get the, and I think you have the answer in the PDF that paper, and message me what did you get this one. Or if you have any doubts or how to get, see, when the object is parallel beam is incident, you have to take object distance as infinity, that's all. When parallel beam of light is incident on a glass sphere, object distance is infinity. You ask the first surface, if parallel beams are incident, ask the first surface, are you receiving rays of light? Yes sir, they are parallel. Where is the object? They don't meet at all, sir. Produce them backwards, they don't meet at all. That means object is at infinity. You have to take u equal to infinity. And another thing is, this is not air, this is water, 4 by 3. Glass is 3 by 2. So both the mediums, N1, both the media, N2, N1, both have refractive indices. So try to solve this, get the answer. If you get the answer, okay, happy. If you are not, don't get the answer, then also you are happy. You have some doubts, message to me for this number, WhatsApp message, I will solve it. Okay? So very, very important problem. And this teaches you lot of patience, at least. Finally, even if you don't get the answer, you will get a lot of patience. Because with lot of patience you have to solve it. Negatives, positives, medium changing. But there is a lot of pleasure out of it, because you will be very accurate in solving this. This is like waving some cloth, right? You should be very accurate, right? You should be very particular. So solving these problems, I don't know whether they will, they are needed in the next life or not. That is not more important. That will teach you a lot of patience to your brain, and you will be more accurate in what we are doing, any work that you do. You know, the people who go to space, they will be given different work before going to the space. They will be asked to wave something, wave some threads and some cloth, because they must get concentration. So what is the need of teaching waving some cloth for a person who is going to the space? Why should he be trained like that? Because they must get concentration. And even under pressure, they must be able to work with patience and with lot of calm mind. So this is also something like that. That will teach you a lot of patience, and you will be very calm, and even when the stress comes in your life, you will be able to face it. So that is what we will get. I'm just giving some connections to your life. So even though if you don't get the answer, don't worry. You think in a different direction or ask me, I will answer it. So we will take this as homework. Try this. All the best. Do well. And if you don't get the answer, we will try it in the next problem. So keep going well. Be cheering. We will meet in the next class with Lensmaker's formula.